Hi guys, welcome back to chemistry. Well, we're not at Canyon High School anymore, and so we're all learning at home. And so through this video, we're starting a new topic today over gases, and I decided to film this video out in my shop because there's a lot of stuff that you might have at home, in your garage, in your shop, that pertains or relates to this topic that we're about to be going. So we're starting the topic of gases. And by gases, I don't mean gasoline like you put in your car or your lawnmower. I'm talking about gas as in solids, liquids, and gases. So over here, off to my left, there's a cutting torch. So we got the oxygen, the green oxygen tank, which has compressed air in there, compressed oxygen. And then next to it is acetylene. You might remember I did a demo with acetylene, I think it was around in January or February, where I made this gas and walked around with Erlenmeyer flash, and y'all could smell it if you wanted to. It kind of smelled like garlic. Most people thought it smelled horrible. And then we did it in captured in a balloon. And then when we lit the balloon, it exploded with this real black sooty smoke. So that's what acetylene gas burns with the black sooty flame. And then you use the oxygen to create an oxidizing environment where you can literally burn through metal. Next to there, I have an air compressor. Y'all might have one at home in your garage. You might have a big tank air compressor. You might have a smaller, like 4.5 gallon one like that. You might have one that plugs into a cigarette lighter in your car to air up your car tire in an emergency, but it just compresses the outside air, whatever the outside air is made up of, into a compressed amount to air up a basketball, a tire, volleyball, whatever it might be. You might have a welder at home. Here I have a MIG welder, and there's a tank of argon and carbon dioxide gas. You might have did some welding at home or at school with a MIG welder, maybe a TIG welder. I have a fish cooker here. And then next to the fish cooker, there's a propane tank, right? Propane tank like you might have on your barbecue pit. So propane, you can also get it in little containers that look like this. You might have these at your deer blind if you go deer hunting, a little heater on top to keep you warm. Here's another propane cylinder. This one is a blue one, but both of these, there is propane in here that is compressed until it became a liquid. And then when you open the valve and let it out, hopefully you can hear the gas coming out, and then you ignite it on fire. Some other examples of gases you might have at home. Right now with this whole coronavirus thing, you might be using more Lysol, disinfectant sprays. So it's in here as a liquid, and then when you spray it, it comes out. You might have some dust off. You might use it to clean the keyboard on your electronics. And so there's gas in there compressed, and then you just, and the gas comes out. So there's a lot of different ways that you encounter gases in your real life. So there's this idea called the kinetic molecular theory. And the kinetic molecular theory states that all matter, solid, liquids, and gases, are made of particles that are constantly moving. And a solid, I have this ice cube right here, the particles are not moving very much, and so the ice keeps its shape. If we add energy to it, the molecules are going to start moving, they're vibrating, they start moving more and more until finally they can start moving around their container, around the flat bottom part of the container. They start spreading out to fill the shape of their container. If you keep giving them energy, they move from the liquid stage into the gaseous stage, and the particles have so much energy as a gas, they're just going crazy, they're just going everywhere, and they expand to fill the volume of their container. So on this fish cooker here, I have a black skillet that I've been heating up, so I'm putting on a pair of gloves. And if I bring the skillet here, I'm going to take this ice cube and drop it in there, and we'll see what it does. So I hope you can see it's already starting to melt. And maybe you can see it not just melting, it's starting to vaporize. You can see the steam being given off. The liquid water is starting to turn into a gas, and the gas particles are expanding and leaving the container, starting to fill up the shop. So if we look at gases, there's 4 different variables that affect a gas. The first one is the number of moles. And by moles, we're talking about what we introduced back in January or February. So if you take a bicycle pump, okay, and I need to air up a volleyball. So I have this volleyball. It's kind of, how you can see, it's kind of flat. So if I connect the bicycle pump to here and I start airing it up, what am I adding? Well, I'm adding air, right? But I'm adding a certain amount of moles of air. We could figure out how much the volleyball gains in mass, and therefore we can figure out how many moles of air we put in there. So that's one of the variable, is the number of moles. The second variable that we want to mention is volume. Volume is the size of the container. So this is a 1 pound propane tank. This container is way smaller than the propane tank that you use on your barbecue pit. So they have a completely different volume. This volleyball has a completely different volume than this big blue ball here. So volume is going to be one of the things that's going to affect how gases behave. The next one that we want to mention is going to be pressure. Pressure, you'll learn about in physics, is force per area, force per unit area. And pressure comes from the molecules of gas hitting against the size of the container. There's a lot of different units of pressure. For volume, I should have mentioned, volume tends to be measured in milliliters or liters, milliliters or liters. Pressure has a lot of different units. There's things like PSI, pounds per square inch, kPa, kilopascals. And you might have encountered these before if you look at an air gauge. So I got a couple air gauges here, and if you look at them, this one right here is in PSI. You can see it right above the white arrow. And then this white one here, right below the black arrow, you might see the letters kPa and also PSI. So it has two different units. There are other units of pressure as well. There's something called millimeters of mercury, mmHg. There's torr, there's atmospheres, there's bars. There's several different units of pressure that we are going to be working with. The last one that we want to mention is temperature. The fourth variable that affects the gas is the temperature. Temperature, if you go back to our heat unit, temperature was a measure of the average kinetic energy of the particles. Kinetic means moving. So how much the particles are moving. The more the particles move, the higher their temperature. The less they move, the lower their temperature. So the four variables that affect the gas are moles, volume, pressure, and temperature. And all these variables can affect each other. If I take this volleyball, and I squeeze it, what am I doing to the volume as I squeeze it? Well, the volume gets smaller, right? You can see it gets smaller. So as the volume gets smaller, what about the pressure inside that ball? Well, the pressure is going up. So when volume is going down, pressure is going up. Well, what if I let some of the air out? Well, then when the pressure goes down, the volume goes back up. So there's an inverse relationship between pressure and volume. So in this container right here, this dust off, you got a gas trapped in there. When you let some of the gas out, what are the remaining gas particles going to do? Well, they're going to spread out. They want to fill their container. I remember I shared a room growing up with my brother, and then when my brother moved off to college, well, then I spread out and took over the whole room, right? I had the whole room to myself, not just half of it. I spread my stuff out. It's the same thing with the gas. When some gas particles leave, the other ones are going to spread out. Well, how does that affect them? Well, when there's a bunch of gases trapped in there, they're bumping into each other, they're banging into each other, they're banging into the walls. It's like when you're back at Canyon High School and you're walking down the hallway and there's 2,800 kids and everybody's banging into each other. You know, there's a lot of friction there. Well, when these particles leave, these other particles spread out and there's not as much friction. They're not colliding with each other as much. And so therefore, the temperature goes down. So by letting some of the pressure out, we're letting the temperature drop. So pressure and temperature move in the same direction. And we can measure that actually. Here I have a laser thermometer. And so if I turn it on and we aim it at the dust-off can, you can see it says it's 73.7 degrees. If I let some out, and now we measure the temperature of this can, 63.5, right? 57.9. What is happening to our temperature? It's going down. As the gases leave, the other gases have more room, and so their temperature drops. Now, the opposite is true. On this air compressor, it was 71.5 degrees earlier, and I turned it on in the shop, and the air compressor filled up with air, and I measured the temperature, and it went to 95 degrees. As you're cramming gas particles in there, they're colliding with each other more, they're hitting the sides of the container more, and their temperature is going up. So there's a direct relationship between pressure and temperature. I thought I had something else I wanted to mention. Okay. If you were to take this Lysol can or a spray paint can, any kind of aerosol can, and you were to throw it in a fire, not that you would ever do that, that'd be stupid, right? But if you would, what would happen to these molecules? Well, they're going to be moving around, increasing in pressure, but the volume of this can is fixed, right? It's 12-ounce can. It can't get any bigger, so the pressure is going to build until finally, and the can is going to explode, right? So as pressure goes up, temperature is going to be trying to go up as well, and temperature is going up, pressure is trying to go up until finally it explodes the can. That's true with this acetylene cylinder here, this red acetylene cylinder. Right here, there's a safety plug here. It actually has a small lead, like a core in there, and in the case of a fire, that lead is going to start melting a little bit over 200 degrees, and it would relieve the pressure in there so you wouldn't explode that tank of acetylene. That would not be a good thing at all. Okay, so now that we kind of have a better understanding of how these gases work, we can use something like this to help us remember these relationships. And I don't have moles on this one, but what I have here is I got pressure, temperature, and volume. So pressure, temperature, and volume. And we can hold any one constant and see what the others do. If I hold temperature constant, if I raise the pressure, if I increase pressure, what will my volume do? Pressure goes up, oh, volume went down, right? What if I lower the pressure? Volume goes up, right? Okay, what if I make my volume smaller? The pressure goes up. What if I make my volume bigger? The pressure goes down. Okay, let's hold pressure steady. Now, when temperature goes up, volume's going up. When temperature goes down, volume goes down. And you see that with car tires a lot in the summer. Temperature goes up, you got your pressure steady in your car, 35 psi, whatever it might be. Temperature starts going up, the car tires get bigger and they end up having more blowouts. And we can hold the opposite. Let's hold volume steady. Temperature goes up, pressure goes up, more blowouts in the summer. Temperature goes down, pressure goes down. Your car tires tend to have less pressure in the wintertime because the molecules of air are cooler, they're not moving as fast, they're not colliding as much with the sides of the tire or with each other, and so you have a lower pressure until you drive your car for a while and you heat them up. Okay, so now you kind of have an understanding of what's going on with moles, pressure, temperature, and volume. Now what we want to do is take a look at mathematical relationships between these. There are 7 different gas laws that we're going to be working with over these next few weeks on this unit. And so today we're going to look at the first 2. We're going to look at one called Dalton. You might remember John Dalton from the atomic theory. So we're going to look at Dalton's law, and then we're going to look at one called Boyle's law. Okay, great. Let's go.